Hey guys, welcome back. So let's get into our last topic, this free energy thing that we're going to be talking about. So, chapter 17, the rest of this that we're going to be talking about, the second law of thermodynamics, Gibbs free energy, and the free energy and chemical equilibrium. So, a couple of things that we're going to be talking about in there. Okay, let's get to it. Questions, comments, problems? Email, phone, WebEx. Let me know. Please talk to me about it. So let's talk about Gibbs free energy. Okay. So if my main goal as a chemist is to predict if a reaction will occur or not, then both enthalpy and entropy are not sufficient for me to do that. Okay? There's not enough information for either one of those for me to be able to say definitively that yes, it's going to occur. Now, I also know that negative T times the delta S of the universe is equal to delta H, the enthalpy of my system, minus T times the entropy of that system. And that has to be greater than 0 for a spontaneous reaction. Okay, so that has to be true. We can rewrite that as delta G, this whether or not this is going to happen, is delta G is equal to delta H minus T delta S, where delta G is the Gibbs free energy, or the energy available to do work. That's actually another way that we define Gibbs free energy. Okay. Now, as always, this calculation can be done from the energies of formations of materials. So sum of the number of products times the delta G for each product minus the sum of the number of reactants times the delta G for those reactants, where delta G0 is the standard free energy of reaction. This is 1 atmosphere pressure for gases, pure liquid, pure solid. Element delta G naught F is 0, and solutions are 1 molar in concentration. Okay? So that's what we're talking about for what that delta G naught F stands for. Okay. So standard conditions, 1 atmosphere, 1 molar, pure liquids, pure solids, and elements are 0 yet again. Okay, well then what's this? Well, I can see right here that there's a temperature dependence in this, right? And I remember that a delta H that's negative is favorable, and a delta S that's positive is favorable. And so if delta S that's positive is favorable multiplied by this T, that gets subtracted from this delta H, which is negative, then I would expect that if delta S is positive and delta H is negative, then this would always be a negative value. And if that's a negative value, then I would expect the delta G would be spontaneous. And that's actually true. So what we see is that if we look at delta H being negative, delta S being positive, delta G is always negative. The reaction proceeds spontaneously at all temperatures, because that's my favorable set of conditions. So again, if I have a negative value there, positive value there, this is always negative, and therefore it always occurs at any temperature. Okay. Now I have the opposite situation, where this is positive, this is negative, then this is always going to be positive. And that means it's never favorable the way that it's written. It's always the reverse reaction. It's going to be favorable. Okay. So now we've talked about this set right here. And now we've talked about this set right here. So again, delta G is always positive. Reaction is spontaneous in the reverse direction at all temperatures. It is not spontaneous as written at any temperature. Okay, so those are my two extremes. Always going to happen, never going to happen. Then we have the cases where it happens sometimes. And that sometimes is dependent on what our temperature is. So let's think about this. If I have a situation where my enthalpy is favorable, so my enthalpy is negative, and my entropy is not favorable, my entropy is also negative, then as long as my temperature is low, so that contribution is small, then my delta G is going to be negative. So the negative delta H will outweigh the negative delta S at small temperatures. Okay? And that's what we see down here. Reaction proceeds spontaneously at low temperatures. High temperatures, the reverse reaction becomes spontaneous. And that's because we have a negative delta H and a negative delta S. Delta S not being favorable, it has to be low temperature. That has to be a small contributing factor for this to work. Okay. Now, our opposite case, when delta H is the one that's unfavorable, then I need that delta S component, even though it's favorable, to be the bigger part. So that has to happen at high temperatures, right? So at high temperatures, that'll be the bigger component, and that means that that delta G will be negative at high temperatures. Okay, and that's what we see right here. Reactions proceed spontaneously at high temperatures. At low temperatures, the reaction is spontaneous in the reverse direction. Okay, so those are the 4 cases that we have. You should be able to walk through the logic on that. Now, this table, not provided to you. Why? Because I'm going to be asking you if delta H is this and delta S is this at this temperature, is this going to be spontaneous? If delta H is this and delta S is this, what temperatures would make this spontaneous, high or low? Things along those lines are what we're going to be talking about. So we'll go through some examples for that. But this table you will not get, and you will need to be able to walk through the logic on it. So not only will you have to be able to predict it, but you'll have to explain to me why. Okay, and we just talked about the why. Okay, so where it's temperature dependent, it's because that's the bigger factor for the one that either where it's favorable or not favorable. Okay, so that's what we're talking about there. So some practice for you. For the following reactions, determine at what temperatures, if any, the reaction will be spontaneous. Okay, fine. Now, I looked at 2 of these previously. I calculated the delta S for that RBCl gas. Somewhere back here. That RBCl gas is right here, and that was negative 186.9202. So I'm going to copy that. And this is my delta S value. And then that TiCl4, we also calculated that one. And that TiCl4 is this value right here. I'm going to copy this as well. And that is negative, so I need to make, because I didn't get the negative sign, so I need to make sure it's still negative when I'm trying to work with it. Oh, wrong place. There. And this has to go right here. And of course, this is negative. Oh. So that's this one. Making methanol gas from liquid methanol. Now, in order for me to look at this, I have to look at those tabulated values again, right? So I need to have both an enthalpy and an entropy to make this work, okay? So I have my entropies. These 2 are here. These are joules per mole Kelvin. I'm going to calculate the entropies for the methanol gas and liquid methanol. Moving stuff around. So methanol, CH3OH. So Methanol is right here. It does say CH3OH. It does say methanol right there. Methanol gas from liquid methanol. Okay, so my gas is right here. That has a 239.70136 joules per mole Kelvin, and liquid methanol is 127.25344. Okay. When I do that reaction, of course, that's CH3OH liquid going to CH3OH gas. And so products minus reactants, we're going to be looking at 239.70136 minus 127.25344. 239.70136 minus 127.25344. And that gives me 112.4. Okay, and of course, if I want to look at this one right here, I want to go from mercury liquid to mercury gas. Now, before I do that, I know, beyond the shadow of a doubt, that I'm going to have to calculate a delta H for this reaction as well. And so my delta H stuff, I'm going to start looking at this CH3OH liquid going to CH3OH gas. I need to find my delta H values for the liquid and the gas. My delta H for the gas is negative 201.08304. So my delta H is, again, this first column. So that's my gas. The liquid is the negative 239.03192. Now, I'm not going to do anything with that right now. I just want to make sure I write it down so I don't have to come find it again. That's all. So let's go find our mercury so that we can get the values for the mercury. Hg liquid, my entropy value for that liquid is 76.02328. My enthalpy is 0. My entropy is the 174.84936. And my enthalpy is 61.3165. Okay, so products minus reactants on that delta S. $174.84936 minus the 76.02328, and again there's 1 mole of each, so 174.84936 minus 76.02328. That gives me positive 98.82608. And again, that's joules per mole Kelvin. So those are all my delta S values over here on this side. So those are my delta S. I'm going to calculate delta H, and I'm going to put those over on this side. Now, I have delta H values for the methanol that I put right here. And again, it's the same formula as what we talked about previously. So the products minus the reactants. So I have my negative 201.08304 minus negative 239.03192. Negative 201.08304. And I'm going to subtract negative 239.03192. And that gives me positive 37.94888. And that's for my methanol. So this is 37.94888. 0.94888. Okay. I can do the same thing right here for the mercury. And since it's products minus reactants, my reactant is 0, I know that that value right here is going to be 61.31652. We have to look up some values for that RBCl. So remember, it was RB. And this was, again, solid. RBCl solid. And we're going to have our Ti2Cl2 gas. TiCl4, Cl2 is 0. I think that our values for most of these are going to be 0, but let's go look at our RBs. RB. I really should use a search function so I don't have to do this. But okay, fine. RBCl solid. My delta H is a negative 434.59208. And that's the wrong place for that. Sorry. This goes over here. Apologize. And my RB gas is 8581384. And then my Cl2 let me look up my Cl2 and make sure that it's 0. Cl2, 0. And of course, I have to verify in my own head, is that what I did in terms of gas to solid? So I want to go back and look at the calculation that we did just to make sure that that's the exact same equate. So RB gas, Cl2 gas, RBCl solid. Okay, so just verifying that that was what I looked at previously. And while I'm here, we have TiS alpha plus 2Cl2 gas goes to TiCl4 gas. And that actually is an alpha that I tried to write there. It's not great, but okay. So I have all my values for the RBCl2. I'm going to look on my TIs. Ti alpha, again, is 0, which is, I'm pretty sure why I chose it. And that TiCl4 down here, gas, is negative 7, 3.1616, which again makes this negative 763.1616. And that RBCl solid, we'll have to calculate that. And again, that's the negative 434.59208. So that product minus the 85.81384 for the reactant. Negative 434.59208 minus 85.81384. And it gives me a negative 520. 40592. Okay, great. So now I have delta S values. I have delta H values. What the hell was I going to do with that? Why did I need all those numbers? It says determine at what temperature, if any, the reaction will be spontaneous. So I want to know at what temperature does delta G become negative. So I want to calculate where it becomes 0 so that I can see what that looks like. Now, we're going to need a bit of space to do this. I'm going to scroll up just a little bit so that we can talk about that RB reaction, and I'm just going to write it like this. And I know that delta G is equal to delta H minus T delta S. And so I want to calculate what delta G is first, because why not? We might as well do the practice. So I know that my delta H is at negative 520.40592 equals negative 520.40592 minus T times the delta S, and that value right there is negative 186.922. So I could calculate what that value is, but I don't know what temperature that I'm going to do this at, right? So I know that my delta G has to be 0 or less than 0. So I want to find out where it hits that 0. Okay, so I'm going to take that negative 520.40592. So I need to isolate the T. So I'm going to move the T to the other side. T times the negative 186.9202 is equal to the negative 520.40592. And then I can divide both sides by this negative 186. So I take my negative 520, divide that by the negative 186.9202, and that gives me my temperature is 2.784, and that's in Kelvin. Now, is that everything? Or did I make a mistake? Oh, that sucks, doesn't it? Now, what are the units on my delta H? Delta H is in kilojoules. So I have two options. There are two ways that I can handle this. Either one of them works, really doesn't matter. But we have to make sure that we take that into account. So if this is kilojoules, I can either divide the 186.9202 to make that kilojoules, or I can transfer this to joules. Now, I prefer to go to kilojoules. It's just my preference. So I take my negative 186.9202. I divide that by 1,000. And so that changes this to negative 0.186922. And that changes this math, of course. So I still take that negative 520.40592 and I divide that by the answer that I just calculated. That gives me my temperature has to be 2784 Kelvin. And I'm just going to leave it as 4 sig, and I actually should leave it as 0.1. So yeah, I'm just going to leave it at the whole number just because I'm being lazy. I don't feel like figuring it out, which is rude, but that's okay. So do you see what I had to do there? So don't forget that you need to do the unit conversion for your delta S to make that work in this calculation. And that's what we're going to be doing is solving for that T value where delta G is 0, because that tells us what temperature that will work at. And then any temperature above that, it will be negative. So from here up, greater than or equal to 2784 Kelvin, that will work. Okay. So I'm going to do one more, and I'm going to do the TI, this last one right here, for that. And so we're looking at, again, delta G 0 equal to delta H, that 61.31652 minus T delta S, negative 98.82608. But I need to convert that. 98.82608 divided by 1,000 0.098282608. It's not going to let me move it. Damn it. (61.31652). I'm going to divide that by the answer that I calculated. And that tells me that when my t is 620.448. 1, 2, 3, 4, 5, 6, 7 Kelvin, then this particular thing becomes negative. Okay, and that's again because my delta G or my delta H is not favorable. So this needs to be at a high temperature for that to happen. So again, it's greater than or equal to that. All right. Now, and this one, on the other hand, is going to be less than or equal to, because as long as it's less than this value, this delta H will be enough to carry this and make it spontaneous. So this one's going to be less than that temperature because that's where it flips to become positive. Here, this is where it flips to become negative. Okay, so remember that when you're calculating your other two values. So I will allow you to calculate those two values, and I will talk to you shortly. Yeah, because we're going to have some more practice. So I'm going to stop here, and I will talk to you soon.